Hello again, grade sevens. In today's lesson, we're actually going to do something that we have done a little bit in the past, which is going to be evaluating expressions, which is essentially just going to be the same thing as taking a mathematical equation and then plugging or substituting numbers in to evaluate a particular expression. And the learning outcome is to evaluate an expression given the value of the variables. Okay, so we're going to jump right into some examples. Like I said, we already do have some familiarity with this. So example 1, given the expression 2y plus 4, I want to evaluate the expression using the substitution method. Okay, the substitution method would just involve using my 3-step procedure, which means step 1, write the equation, step 2, substitute in the variable, the number, and then step 3, just evaluate and calculate what the expression is equal to. So let's go ahead and do this. Okay, so I'm not going to call it an equation, it's an expression. An expression is a combination of numerical coefficients, variables, and constants. So this is the expression I'm going to look at, 2y plus 4. So I want to evaluate the expression when y equals 1. So the way I would do that is, first of all, write down the equation, although let's expand it a little bit to show the operation between the numerical coefficient and the variable. So that would be 2 times y plus 4. Okay, so that's step 1. Step 2, we're going to do a substitution. So the substitution is I'm just going to take the y equals 1 and just replace the y and the expression with that value. So when I do that, I would then get 2 times 1 plus 4. And now we need to carry out the correct order of operations. So what do? Do you go 2 times 1 first or 1 plus 4? Well, going back to the order of operations acronyms, we have BEDMAS. This tells me you're always going to do the multiplication first. We'll do 2 times 1 first, so then that would be 2 times 1 is 2 plus 4. And then 2 plus 4 is, of course, equal to 6. So that is that's the expression evaluated when y equals 1. Okay, let's change the variable to something else. And again, that's why it's called a variable, because we can use different numbers to plug in for it, depending on the situation. So y equals 3. So then we'd have 2, write the equation, times y. That's supposed to be a multiplication symbol, but it looks like, I don't even know what that looks like. Let's just draw it again. Whatever that was, it was so bad that I can't even describe it in words. Okay, so I have 2 times y plus 4. Okay, and then this time around, we're going to take the y equals 3. And we're going to substitute it in for the variable y. So when I do that, this would then be 2 times 3. Y is a value of 3 plus 4. Carry out the order of operations. 2 times 3 is 6 plus 4 would then be equal to 10. Okay. Like I said, we've pretty much done this before, except we did it with equations instead of expressions. Now, because we are expected to do this visually, we're also going to do this using cups and counters, which I'm not the biggest fan of using these visual techniques of doing things, but anyways, it does serve a purpose. So let's just go ahead and just get it over with. Okay, so just a quick reminder for cups and counters. So when you draw a cup looks something like this. And the number of cups you draw is going to be represented by the value of the numerical coefficient. The counter is just a little tiny circle, and that's going to be represented by the value of the constant. Okay, so first things first, let's just take the expression and let's draw it with cups and counters. Then we'll worry about evaluating the expression. So just drawing it strictly with cups and counters, we'd have 2y plus 4. So the numerical coefficient is 2. So the numerical coefficient equals 2. And again, that's going to be the number of cups we draw. And the constant is 4, and that's the number of counters. So if I draw this with cups and counters, I'd have 2 cups. So 1 cup, 2 cups, and then add 1, 2, 3, 4 counters. 2 cups plus 4 counters. All right. Now, the way we need to evaluate it is if it says if y equals 1, what that wants me to do, so I'll write down what I'm going to do here. So let's say for y equals 1, what I'm going to do is I'm going to drop 1 counter into each cup. So that's how we're going to evaluate it for using cups and counters. Whatever the value of the variable is, that's going to tell you how many counters you're going to drop into each one of these cups. Okay, so if we draw this, this would then look like, so here's 1 cup, here's a 2nd cup, and we have the 4 counters. So if y equals 1, I'm going to drop 1 counter into each cup. So we'll drop 1 counter into this cup, we'll drop 1 counter into that cup. And then to evaluate the expression, all you need to do is count the total number of counters, including the counters in the cup. So if we look right here, how many total counters do we have? Well, we have 1 in the cup, 1 in the 2nd cup, and we have 4 other ones. So we have 6 total counters. And just note, that's the same thing as the answer here. Okay, we just did a different method. We just did it visually. Okay, well, how about for y equals 2? Okay, so we'll do B. Okay, so if y equals 2, what we want to do is now we're going to drop a different number of counters into each cup. So instead of dropping 1 counter into each cup, this is y equals 3, not 2. We're going to drop 3 counters into each cup. Okay, so let's draw the cups and counters. So I would have, here's 1 cup, here's a 2nd cup, and then we're going to add this to 1, 2, 3, 4 counters. Now this time around, I'm going to drop 3 counters into each one of these cups. So I would drop in 1, 2, 3. So that's all the valuable, when you're evaluating it, whatever the value of the variable is, that's number of counters to drop into each cup. So you'd have 1, 2, 3. And now we just count the total number of counters. So I have 1, 2, 3 in this cup, then 4, 5, 6 in that one, then 7, 8, 9, 10. And if I count the total number of counters, that's what the expression is evaluated to. So in this case right here, 3 plus 3 plus 4 would be 10 counters. Okay, and if you look up here, that's the same thing as the answer when we use the substitution method. Okay, so the cups and counters are okay right here, but if you get like a huge expression, like maybe like 3y plus 100, you're not going to draw 100 counters. Like that'd be insane to like waste that amount of time to do it. But I guess the point of it is it's just trying to like get you to visualize the difference between a numerical coefficient and also between a constant. Because again, they're they're not the same thing. So there is a difference in some of these values. Sorry, that 3 was annoying me. I want to redraw it. Okay, let's go to example 3. It says the number of line segments that form the squares can be described using the expression 3s plus 1, where s is the number of squares. And what I want to do is create a table of values for s and 3s plus 1, use whole numbers of 1 to 6 for s. Okay. So let's do this. So let's make a table. First of all, I'm going to label the figures. Let's call this guy figure 1. Or you can call it shape 1 if you wanted to. I'll call this one figure 2. And we'll do this one's figure 3. Okay, we'll do a table of values with 3 columns. So we'll do, first column is going to be the figure number. The second column is going to be the number of squares. And that's going to be S. And then we also are going to make another column for the expression 3s plus 1. Okay, so let's just make a horizontal line, do a couple of vertical lines to complete the table. Okay, and we're going to do this for, it says use whole numbers 1 through 6 through s. So we're going to do figures 1 to 6. We have 1, 2, 3, 4, 5, and 6. Okay, the number of squares, well, you can just count them. So figure 1 has 1 square. Figure 2 has 2 squares, so you have 2. Figure 3 has 1, 2, 3 squares. So we can immediately see the pattern with the number of squares. Figure 4 is going to have 4 squares. Figure 5 is going to have 5 squares, and figure 6 is going to have 6 squares. Okay, so to get this column here, we actually need to evaluate this expression using different values of s. So first one we're going to do is we're going to use s equals 1. And I'm going to plug s equals 1 into the expression 3s plus 1 and evaluate it. So now we use our 3-step procedure. So step 1, I write down the expression. So 3 times s plus 1. And we'll just do a substitution here. So the substitution is I'm going to take this s equals 1, and I'm just going to replace it with the s that you have there. So then this would be 3 times 1 plus 1, and 3 times 1 plus 1. 3 times 1 is 3, plus 1 is going to be equal to 4. So when s equals 1 in the expression, then 3s plus 1 is going to be 4. Okay, let's do it for s equals 2. S equals 2. Let's plug it into our 3-step procedure. So we have 3 times s plus 1. This time around, we're going to replace s with 2. So when I do that, you're then going to have 3 times 2 plus 1. Okay, order of operations, 3 times 2 is 6, plus 1. And that's going to be equal to 7. So when s equals 2, 3s plus 1 is going to be 7. Okay, let's do one more, and then at that point we should be pretty certain about what the rest of the pattern is. So let's do s equals 3. So then we're going to go 3 times s plus 1. And this time around, we're going to replace s with 3. If I replace s with 3, then this would turn into 3 times 3 plus 1. 3 times 3 is 9. Plus 1 is equal to 10. Okay, so let's fill it in. So we have a 10 here. Okay, at this point, we could continue to evaluate the expression for s equals 4, 5, 6, but now we should be able to identify the pattern. So what's going on at the 3s plus 1 values? Well, for every next shape, we are going up by 3. So 4 plus 3 is 7. 7 plus 3 is 10. 10 plus 3 would be 13. 13 plus 3 would be 16. And then 16 plus 3 would be 19. Now, I should point out that, well, what does this expression represent, 3s plus 1? It represents the number of line segments in the shape. So we can count this and check. So let's use a green pen. Okay, figure 1, how many line segments make up the square? So it'd be the number of like these little lines here. So that'd be like 1, 2, 3, 4. So yep, that one's got 4. This one has 1, 2, 3, 4, 5, 6, 7 line segments. Again, that's confirmed there. And in this figure, it'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, that's also confirmed. Okay, now I'm going to do one more example. I realize that the notes booklet doesn't have this example in it, but we can just add it in here. So it's going to allow us to solve another problem from the homework I'm about to assign. So this one says, make a table of values for the expression 2x plus 5 and use whole number of values of 0 to 4 through x. Okay, so this is pretty similar to the previous example, okay? But this time around, it doesn't show us any figures, so we don't know what the actual, we don't know what this expression is representing. Okay, so we'll do a table where in the first column, I'm just going to write down values of x. And the second column, I'm going to write down values of 2x plus 5. Okay, we're going to do values of 0 to 4 through x. So I'll do 0, 1, 2, 3, and 4. Okay, so to get the value of 2x plus 5, we just need to do substitution of these values of x into that expression. So the first one would be, again, whenever you have 2 and a variable beside each other, it's just going to be 2 times it. It's always multiplications. We'd have 2 times x plus 5. Oops, actually, let's identify which variable we're going to sub in first. So let's just quickly erase that. Go back to the pen. Okay, so we're going to start off by validating the expression when x equals 0. Okay, so when x equals 0, let's evaluate 2 times x plus 5. Okay, so we're going to replace x with 0, so then that would be 2 times 0 plus 5. 2 times 0 is 0, plus 5 would just be equal to 5. Okay, so this is 5. Now let's evaluate it for x equals 1. So for x equals 1, we're going to evaluate 2 times x plus 5. Okay, so we have 2, and we're going to substitute in 1 for x. So we're going to do 2 times 1 plus 5. 2 times 1 is 2, plus 5 is equal to 7. So let's fill it in the table. We'll do one more, and then we should be able to identify the pattern after that. So then we have x is equal to 2. Go to my expression, 2 times x plus 5. We're going to replace x with 2, so we go 2 times 2 plus 5 would be equal to 2 times 2 is 4, plus 5 is going to then be equal to 9. So we have 5, 7, 9. Now, to get the value of 2x plus 5 for 3 and 4, we could do substitution, but again, at this point, we should be able to identify the pattern. So what's happening to the 2x plus 5? expression as you keep increasing x by 1? Well, we're going from 5 to 7 to 9. We're just adding 2 every single time. So we starting with 5, add 2 to get to the next term in the expression. So 9 plus 2 would be 11, and then 11 plus 2 would be 13. Okay, so you can complete in your MathLink 7 textbook, pages 368, 369, numbers 5 through 13. Yeah, it seems like it's a lot of work, but a lot of them are just really simple questions where you are asked to model, just draw a picture with cups and counters, or it shows you the cups and counters and it just wants you to just write the expression down. And then you start to get into the substitution work that we talked about in today's lesson. And then in the next lesson, we're going to wrap up the unit study by talking about linear relations, which we've actually already been dealing with, although we're going to start to graph the linear relations. And I'll talk to you then.